intermediate inputs at home to be able to produce things. And now maybe more of those intermediate inputs are tradable, and that means that more products are accessible at lower levels of person bytes at home. So you can get into production with fewer person bytes that you could before, and then maybe I'm just launching that as a hypothesis. So finally, I would like to stress that coordination failures in the accumulation of productive knowledge seem to play an important role in preventing development and in explaining the great divergence that characterized the 200 years since the 1800s. That analytically, this is something that is not easily solved through big push policies. So it's not like in these big push policies you say, well, there are two equilibria, so if I focus on the good equilibria, I get all the good things, because this productive knowledge space is very dense, it's very high dimensional, so it's not obvious that a big push, that there are two equilibria, there are an infinity of equilibria, and that just big push is going to do it for you. There's more nitty-grain coordination than that. Understanding the changing topology of this product space is an important area of future research. And as is the understanding of what are the country characteristics that, in spite of the shape of this product space, in spite of the shape of technology, makes some countries be able to advance more quickly than others. I couldn't find much traction to stories that are based on finance, education, or governance, but maybe other things like migration or foreign direct investment or public-private coordination mechanisms might show in the future more traction in terms of explaining the speed at which countries grow and develop. Thank you very much.
Thank you, Professor Hausman. I know that everybody needs a little bit of caffeine now in their blood, but let me give you a quick facts here of what is going to happen in the following hours. So a couple of things. There are a lot of students with white t-shirts. They know everything about the building, so they are going to be your information points there. After these 2 or 3 minutes that I'm going to speak, we're going to give you some coffee. So just walk down outside this area, and the coffee will be over there. Also, we'll be serving coffee inside the building. So there are 2 spots that you're going to have coffee. Not everybody has their program with them, so we're going to give all the programs for those that not have it. Otherwise, it's inside your bag. We're going to give those programs at the lunch time. So when you are going to get and grab your lunch, we're going to give you also the program and the invitations for all the social events. And probably this is the most important thing for today. Your entry to the La Moneda Palace, it's going to be the credential. You don't need the invitation. You just need to wear this thing. So for those that haven't registered yet, the registration will be open until 3 p.m. So go there, register, and you're going to have your credential with you. After the coffee, we're going to have 3 invited sessions. One is going to be here in this area. The other one, it's going to be in the room 300, that is downstairs that way. And the other one is going to be in room 304, that it's just across this door inside the building. Also, there is an information point over there. So we're going to have those invited sessions. After the invited sessions, we're going to serve lunch. Lunch is going to be served downstairs, this coffee shop. It's going to be served the lunch. It's in a lunch box, so you can move around, gather, chat with your friends and everything. And after that, we're going to start the afternoon with the contributed sessions and everything. On the contributed sessions, we don't have discussants. So each of you that are going to be presenting there, hold your times, and you are the ones that are the owners of those sessions. We're gonna, today's meeting, we're gonna end at 5:30 sharp, because we have to take buses to La Moneda. We are gonna be leaving from here at 5:45. So we expect to arrive La Moneda around 6:30, 7 p.m. So please, for those sessions that are gonna be in the afternoon, that are just before leaving to La Moneda, we need everybody to finish at 5:30 p.m. Every question that you might have, I'm Fernando Larraín. I'm going to be moving around. You can ask me, but there are all white T-shirts from students that you can ask there. Enjoy, have fun, and we expect that you have a lot of fun here in Chile and Universidad Adolfo Ibáñez. Thank you.
And it was called yellow. So then I took my turn.
And so I want to just tell you for a minute about our organization. Oportunidad was founded about 5 years ago by Andrónico Luksic here in Chile. And our objective is to improve early education here in Chile amongst people who have limited resources, especially in the pre-kinder and kinder years. And we're doing that by working with Harvard School of Education. And with them, we have been in quite a few schools around Santiago, focusing on teacher training and capacitation, working with the families so that they will know more about how to stimulate their kids to learn better at the home, and by providing some materials to the classroom. Anyway, our project has both control groups and groups that are receiving the intervention. And so therefore, the evaluation piece is really important to us. And for that, we've been working with Diego Portales University. In any case, since we're also interested in impact evaluation, I'm honored to be hosting this panel. And now I pass it over to Eduardo Feinsilber, who will introduce our distinguished panelists. Thanks for being here, and have a great day.
Welcome everybody. This is a very special session. I was just teaching instrumental variables this morning, and I told the students that all the things I were teaching were people were sitting here. So we're going to go overboard 10 minutes, so we're going to have 25 minutes presentation and 5 minutes for discussion. I will be keeping track of the time. First, we're going to have Joshua Angrist presenting the elite illusion achievement effects at Boston and New York exam schools. This is very interesting for Chile, as you might know, because it's related to schools, public schools that have a strong selection system because they are very attractive to students, which is a little bit like excellent schools in Chile. We're going to have a paper by Guido Imbens, identification and inference with many invalid instruments. So everything I taught this morning was essentially wrong, given this paper. And Victor Lavi is going to present how responsive is investment in schooling to changes in redistribution policies and in returns. Okay, so thank you and have a good one.
Thank you very much, Eduardo. Thanks for inviting me. Eduardo, Andrea, and Amelia, it's a pleasure to be here. It's my first visit to Chile, and I'm looking forward to seeing some of Santiago and the country. The paper I'm giving today is called The Elite Illusion, Achievement Effects at Boston and New York Exam Schools, and it's joint work with Attila Abdulkadiroglu from Duke and my MIT colleague Parag Pathak. As Eduardo mentioned, I think this may be of some relevance for education policy debates in Chile. Perhaps I'll learn more about that from your questions if we have time. So let me quickly tell you what we're studying here. We're studying something that is known in the American lexicon as an exam school. An exam school is a public school with a competitive admissions exam. Boston and New York run the most famous long-standing exam school programs. We have some others, relatively unusual in the United States. Exam schools are very controversial. They generate concerns about elitism. And anytime you talk about education in the United States, that always spills over into discussions about race and racial differences. So the selectivity of the exam schools tends to produce a fairly segregated environment. The question we're asking here is what's the effect of the exam schools? Now, of course, exam school students are clearly much higher achieving than their public school peers. That's a descriptive fact. The question that we're trying to address in this paper is what's the causal effect of achievement at Boston and New York exam school attendance, and we'll be looking at what's the causal effect of attendance on achievement, and we'll be looking at a variety of outcomes, but I won't have time to discuss most of them today. I'll focus on test scores, and I should say also that I won't have time to report the results for New York. I'll focus on Boston. How do we answer this question? Well, we don't have a randomized trial, but we have something pretty close, pretty good. We get to do RD, and it's a very nice, clean setup. Let me give you a little bit of background about Boston's exam schools before we jump right in. Boston has three traditional exam schools. The oldest is Boston Latin School, which opened in 1635. Boston Latin Academy from the 19th century, and the O'Brien School from the 19th century. BLS, as we call it, the Boston Latin School, is the oldest public high school in the United States. And it really is the beginning of the expansion of high school more widely. BLS sometimes boasts that Harvard University was created so that BLS graduates would have something to do when they finished. BLS routinely appears in rankings of the best schools in the country, like the U.S. News and World Report rankings. As I mentioned, people always talk about race in public school context. There was a period when exam schools used racial quotas. That began in 1974 when the Boston public school system came under federal court control. That ended in the 1990s. So the data we're looking at are after the period when racial quotas were in place, but I'll still have something to say very briefly about race. What do the exam schools offer? Well, they offer more advanced courses, but they have larger classes. Let me give you a very quick look, kind of descriptive. I hope you can see this. I assume the slides are projecting. How's it look, guys? You can see it. So I'll just show you very quickly some facts about the schools. One thing I want to mention is the way we quote the scores here. All the scores here are standardized to the Boston Public School mean and standard deviation. So the scores, the outcome scores, and the baseline scores have a mean of 0 and a standard deviation of 1. So what I'm showing you here, is that the overall mean in Boston is negative in the traditional schools, because I've taken the exam schools out, but the mean scores are strongly positive in the exam schools, and that just reflects the highly positive selection in the exam schools. If we look at some other facts about the schools, like the student-teacher ratio, it's interesting to notice that class size is larger in the exam schools than the traditional schools. Another interesting feature of the exam schools is that the teaching staff is relatively senior, as they say. The teachers are older. So for example, a fifth of exam school teachers are over age 56, while that number is much lower in the traditional schools. And that reflects the fact that teaching positions in the public school system in the United States are typically allocated by seniority. Exam school positions are desirable positions. And so the more senior teachers get those. I have some information about New York. I think I'm going to skip it because we're not going to have time to get to that. What's the exam school treatment? That's a natural question that you might be asking yourself, or that you would ask me if we were discussing this. So, it's not entirely clear. There's a number of ways to think about it. One thing that is clear that I'll show you is there's a kind of a peer effect. Exam school students study with peers who are like them in the sense that they have very high levels of achievement. They're selected that way. So there's clearly a peer effect. We could also think of it as an element of tracking, since we're grouping relatively homogeneous kids together, high achievers. There's also some special programs for high achievers, like math and science competitions and other enrichment activities. There are some resource differences. Some of the exam schools have excellent facilities. I should say that's not uniformly true, particularly in Boston. And then there's these other dimensions that I showed you. More senior teaching staff and exam school classes are larger, and that's true both in Boston and New York. Since the resource comparison is really kind of mixed, we see the exam school experiment, in quotes, if you like, as mostly informative about a combination of peer and tracking effects. Let me now talk very briefly about the data structure. The data for the Boston study come from administrative records for the entire city. We have every child who was ever enrolled in a Boston public school. We have some demographic information about that child. And then we have the outcome. The outcome is what's called the MCAS score. That's a standardized testing program that runs in the state of Massachusetts. There's two ways to enter exam schools. You can either enter in 7th grade or 9th grade. Most applicants enter in 7th grade, so that's what we call middle school. And then we're going to follow those cohorts of applicants through as they're tested in middle school, 7th, 8th, and then in high school in 10th. We're looking only on applicants who are coming from the regular Boston public school system. And so really we're asking a very specific question. How does an exam school education compare to a regular Boston public school education? Okay. In fact, what's going to be going on here is a little more complicated than that. It's really going to be kind of an incremental treatment effect because the exam schools are staggered in terms of their selectivity. The easiest exam school to get into is O'Brien. The next one up is Latin Academy. The next one up, the most selective, is Latin School. So what the RD design does for us is identifies the causal effect at each increment there. And you'll see that very clearly in the plots. And then we'll put a little bit of structure on that, not too much. Fuzzy RD, which as Eduardo knows, is instrumental variables. So we'll get to do some instrumental variables. Okay. I'm not going to spend much time on the demographics. I'll just mention that the Boston Public School District, like other urban districts in the United States, it's a heavily minority district, mostly non-white students, mostly children from families that are poor enough to qualify for a subsidized lunch. About a fifth of the students come from what's called a limited English proficiency background. That is, they're not native English speakers at home. And of course, another descriptive fact, which we've already seen, is that the exam school kids are highly positively selected. That's really just mechanical. Okay, so we'll skip the descriptives and we'll go right to some plots. Well, let me give you a little bit of background before that you need for understanding the plots. So take the population of applicants for spots in grade 7, grade 9. The students rank the schools that they would like to go to. So there's a two-sided matching problem here. The students rank the schools they would like to go to on one hand. Then on the other hand, the students themselves are ranked by a composite. The composite is a weighted average of your GPA, your grade point average, and your score on a test. The exact formula which produces this composite is a closely guarded secret. We don't actually know what the rank is generated by, but we know the rank. In other words, we know how you were ranked. So that's all we really need to do RD. Then what happens is, essentially, each school goes down the list. There's something, again, a little more complicated going on because it's two-sided matching. There's deferred acceptance that allocates the students, a kind of a matching algorithm. But basically, you can punt on all that and just think about every school has a list. There's the minimum ranked kid at that school that gets in. Nobody below gets in. The kids above get offers. Not all of them actually go. Okay, so the lowest rank that you get an offer at a given school is CK, and then we like to standardize that. So we're going to measure relative to the cutoff. So the standardized rank is RIK, the rank at the school, the kid's rank at a particular school, minus the cutoff divided by the range. And that's going to facilitate our graphical analysis. I'll start with some plots. The plots will have just a raw CEF, raw conditional mean function, and then smoothed using the Imbens-Kaya-Raman bandwidth, and we'll also use that for estimation. And we'll just do that in a kind of a window around the cutoff. So let me start with what we think of as the first stage. So here are the Boston first stage plots. So what you can see here very clearly, again, remember, there's 3 schools, so there's 3 ranks. Applicants to each school, the applicants have to decide to which school they're applying. So at each school, the rank is centered at 0. That's O'Brien, that's Latin Academy, that's Latin School. Now what you can see is what's the probability of enrollment? In any exam school, to the left of the O'Brien cutoff, the probability of enrollment is basically 0. To the left of the exam school, the O'Brien cutoff, the probability of enrollment is basically 0, and then it jumps up to about 70%. Now, what happens at the other exam schools is a little more complicated. To the left of the academy cutoff, the probability of enrollment is not 0 because those kids didn't qualify for academy, but they do qualify for O'Brien. And so they do go to some exam school. And what I'm plotting here is the probability of enrolling in any exam school and not a particular exam school. Now, because academy is more desirable than O'Brien, kids who qualify for academy are more likely to go to an exam school than kids who qualify for O'Brien only. Same thing happens at the Latin school cutoff. To the left of the Latin school cutoff, those kids don't qualify for Latin school, but they qualify for Latin academy. So the probability of enrolling is very high. And in fact, qualifying for Latin school doesn't increase the probability of enrollment very much, though it does increase it some. So you might wonder, how should we think about the first stage here? Here's a variation on that where instead of enrollment, we do it for years. I'm going to skip that. This is really, this plot, I don't have time to go through it, but it shows the anatomy. It sort of shows school by school enrollment at the cutoff, and it shows how what happens as we go to the right of the O'Brien cutoff, the probability of enrolling at O'Brien initially jumps and then falls, but the probability of enrolling at academy begins to rise. So that all sounds kind of complicated and messy. So here's how we make sense of it. And this guides our interpretation of the results in the paper. There's sort of a messiness to the enrollment facts, but it's very clean when we think about peers, okay? What happens at each cutoff is that the average quality of my peers jumps by about half of a standard deviation. And that's because the exam schools are kind of in a hierarchy. So if I qualify for O'Brien, what's plotted here is the peer mean, the average baseline, that's a pre-treatment score. Before application, the average baseline score of the kids that I am in school with in 8th grade, the average 4th grade scores of the kids that I am in school with in 8th grade. That jumps by half a standard deviation at O'Brien. Well, that's not that surprising because there's a big enrollment bump at O'Brien. But it also jumps by about half a standard deviation at Academy because what happens when I qualify for Academy, I move from O'Brien to Academy and the Academy kids are better. Same thing at the Latin school cutoff. When I qualify for Latin school, I move from Academy to Latin school. The Latin school is a much more selective school than the Boston Latin Academy. So again, my peer mean jumps by about half a standard deviation. So we really think of this as the core first stage for this project. The enrollment effects are kind of mixed across schools, but there's a huge increase in peer quality at every cutoff. So we're going to put that together and ultimately, not necessarily something I'll get time to talk about in detail today, but we're going to use that to estimate peer effects. Anyway, that's by way of the first stage. So what I've shown you for the first stage is there are enrollment jumps at the first cutoff. There's a smaller enrollment jump at the second cutoff. There's a little bit of an enrollment effect at the third cutoff, but there are big jumps in peer quality at each cutoff. What about outcomes? Okay, so the outcomes are the post-treatment scores. And here we have a menu of outcomes. The ones that I'll start with are the MCAS scores. These are the tests that kids take in school. And then we also have in the paper advanced placement exams, SATs, the exams that American students take when they apply to college, and a variety of other outcomes that we won't have time to discuss. Well, here are the plots for outcomes. Big jump in peer quality. No discernible change in post-treatment achievement. That's really the bottom line. The nice thing about RD is when it works, it's an easy story to tell. The story that's being told in these plots is, even though exam schools are highly selective, and parents would give at least a kidney and maybe a liver to get one of their children into these schools, the peer quality is dramatically better. Student achievement is unchanged around the threshold. In other words, the exam school treatment effect is essentially 0. And you can see that here. This is for 7th and 8th grade math scores. This is for 7th and 8th grade English scores. This is for 10th grade math scores. This is for 10th grade English scores. Here there is a bit of an exception. It looks like there might be a treatment effect, so that's nice that we can find one when there is one. At O'Brien, there's a little bit of a jump that's marginally significant, and at Latin Academy, there's a bigger jump, and that's marginally significant. So there is something going on. It looks like 2 out of 3 of the schools boost achievement in a particular subject in grade. So that's kind of an isolated finding. An interesting fact about this finding, especially in the American context, and in particularly in the Boston context, is that this increase in 10th grade English scores is driven almost entirely by non-white applicants, the group that's at the heart of the exam school controversy. So a marginal non-white applicant, mostly black, some Hispanic, does see an improvement in high school English scores when they get into an exam school. And I'll show you that very briefly. But just to summarize, first stage effects in the sample of applicants to school K offers an enrollment jump. Enrollment at any exam school also jump. About a half a standard deviation in improvement in peers. No corresponding jumps in outcome conditional mean functions, except perhaps for 10th grade ELA. Okay, the next thing that we need to do in the paper is estimate the jump sizes. So we use both parametric and non-parametric models. This is the parametric model. The running variable is the rank, so we control for polynomial functions of the rank, in this case a cubic, interacted with the cutoff. The treatment effect there is the jump. And then we also do a non-parametric version of that. The non-parametric version of that uses a kind of set of weights that emphasize data near the cutoff, but only use linear control. So the difference between parametric and non-parametric is that we use weighted least squares instead of OLS. The sample may be smaller because we're picking a bandwidth that kind of shrinks in around the cutoff, and we only have linear running variable controls. So let me just show you very quickly what that produces. It produces a lot of numbers. We're not going to discuss every number, don't worry. But basically what you see here is a lot of zeros. In other words, numbers that are statistically indistinguishable from 0. And so it's really about the difference between the estimates and the plots is really just about putting standard errors on those estimates. We'd like to make it as precise as possible. Let me then show you one more thing. I mentioned subgroups. I won't go back to that. We try to interpret this as sort of working through a particular channel so that we can combine all the exam school results together. So the way that we do that is we set up 2-stage least squares. We have the same controls. Now I've bundled that all into X, running variable controls and so on, and then a particular endogenous variable. And as you might guess, my favorite endogenous variable for this problem is the peer mean. So what we're doing here is we're using the exam school cutoff as an instrument for peer quality for students in the neighborhood of the cutoff. And that's why you may have wondered, why did I call that first set of plots the first stage and that second set of plots for the outcome the reduced form? Well, because I know that this is where this is heading. It's heading to 2-stage least squares, as often seems to be the case with me. So let me show you very quickly what happens when you do that. Here our table 6 shows the results. The way we set it up, we can do it in various ways. Here, different endogenous variables, so we can have an enrollment dummy as the endogenous variable. We can have years in exam school as an endogenous variable, or the peer mean as an endogenous variable. Now here we're sort of futzing and putzing because we're not really sure what satisfies the exclusion restriction. It doesn't matter a whole lot because all these effects are 0. So again, it's mostly about getting standard errors. So I'm happy to be able to construct a peer effect which is on the order of 0. Here, this is an over-identified model with a standard error of 0.04. That's what 2-stage least squares lets me do. I can then say, well, I can reject that other guy's peer effect of 0.1, which would be small in the literature on peer effects. So I'm very happy to be able to accomplish that. That's really kind of the point of the 2-stage least squares, is about precision. The paper then goes in a number of other directions. I'll just tell you very briefly. Obviously, we want to look at other outcomes. Some people might say, who cares about MCAS scores? Some test that the state thinks we have to take. So we look at AP scores, Those are important to students. They get college credit when they pass AP. We look at SAT scores. Those are obviously important to students who want to go to college. We look at PSATs. Same set of results. The results continue to show no effects on the other outcome. The last thing that we spend a lot of time on in the paper is a sort of a conceptual issue related to the fact that regression discontinuity methods, by their very nature, focus on kids who are marginal. They're close to cutoffs, and we'd like to do something about that. We'd like to have something to say about that. Maybe the worst kid who gets into an exam school doesn't get anything out of it, but there's sort of higher achieving kids who get something out of it, okay? That's what a lot of my colleagues think. A lot of my colleagues at MIT are big believers in elite education. Well, that's natural since we're purveyors of elite education. And so when I show them this result, they say, yeah, but there are kids who are benefiting from this. Well, the question is, can you do anything about that in an RD setting? And there are a few things that you can do, and I'll only have time to tell you about one of them. One thing that you can do is to recognize that the particular rank variable or running variable that's behind the exam school admissions procedure here is one of many tests. It's not a particularly good test. It's sort of historical, used is what it is. And so conditional on being marginal for that test, there's still a distribution of test scores on other tests. And so what we can do is take kids who are marginal on the running variable, but very high achieving, say, on earlier MCAS. Those might be kids who just had a bad day on the day that they took the exam school test. So they are, in a sense, a legitimate high-achieving group. Well, the results are exactly the same for those kids who are high-achieving on other tests, marginal on the running variable. So that points to some sense of external validity. Okay, well, that's all I have time for. I hope I got you interested. And if you're thinking about opening new exam schools in Chile, which is what I've been told by a number of people, I hope you'll take a look at our paper first. Thank you.
Given the English result on 10th grade, I'm wondering if there are signaling results for outcomes, say admission to college or to jobs. So it may well be small quantitatively, but there may be signaling effects. So if they're being lumped with, so let me put it this way. A child from a higher level school with the equivalent test score is more likely to get it, say, into Harvard than a kid from a generic public school with the same test score.
Indeed, and so it's been said, for example, that Harvard, and perhaps this is for the same historical reasons that I mentioned earlier, Harvard loves Boston Latin School kids and takes a couple dozen of those kids every year. So one thing we would like to look at is higher education outcomes, post-secondary. You might think that even though there's no value added sort of in terms of human capital, there's some benefit to an exam school education through connections or signaling. So we do have some results on that. They're not in the paper, but we've looked at college quality as measured, for example, by the Barron's selectivity, and there's nothing there, surprisingly. Quite striking. I should also add that Roland Fryer has looked at the education outcomes for New York City exam schools, and he likewise doesn't find anything. So it's a reasonable conjecture. It doesn't turn out to be true in this case. Here's somebody behind you, Eduardo. You mean the admissions test? There's something called the ISEE, which is the test that's used to rank the exam school applicants. And then what happens is there's this guy who named Jack who works in the basement of the Boston Public Schools. And he takes that data and he mixes it in with your high school GPA in a secret formula, and he produces a rank. And the rank variable is almost the same for each school. It differs very slightly. So our running variable here, what's interesting is it can remain mysterious. The beauty of RD is you know, wherever the running variable comes from, that's fine, as long as it sort of, people are not manipulating that strategically. And I'm sure Jack is not doing that. So we do have the running variable, yeah, there is that one test. The same thing in New York. The specialized high school admissions test, that's a big part of New York City public school life. There is that one test.
I guess I'll ask one question,
Sure, Eduardo.
which is what probably many people are thinking. Would you say that the results are extendable to the Chilean context? Of course, you have to know more about the Chilean context, but is it surprising a little bit, no? In Chile, we have one big exam school, which is very, very famous, and it's surprising to say, not clear that if you reproduce this in other cities, you're going to have the same result or similar result. So,
Well, I can't say.
would you put your money on the results?
I've only been in Chile for about an hour and a half. So I don't really know that much about Chile yet, though I've been trying to, you know, look out the window and stuff. But you know, it does not surprise me. I guess I should have written it down or put it on a piece of paper somewhere, because I'm very skeptical of peer effects, and I think that parents are easily fooled. And in this case, I think what's happening is that the kids who are good enough to almost get in an exam school are just very good, and those kids are going to do very well in life anyway. And the exam school education is not adding very much. I should add something else since you lead me to that. I think that the group that benefits most from education is the group of relatively weak achievers. And we have evidence on that in another line of work that I'm doing with the same colleagues on charter schools. And I talked about this a little bit in an interview with your paper, El Mercurio, yesterday. Charter schools are publicly funded, essentially publicly funded private schools, but unlike regular private schools, they focus on very low achieving minority children in high poverty urban districts. And a subset of those schools, not all of them, but a subset of those schools have shown that they can produce spectacular achievement gains for the kids at the very bottom of the barrel. And I like to contrast that with the exam school treatment, which focuses on kids who are at the upper end of the achievement distribution. And one reason I like to do that is I think that that casts doubt on the view that human capital is somehow self-generating, that resources at the low end are in a sense wasted, or that if you can't get a kid up to a relatively high level of achievement, you may as well give up on him. In fact, the evidence in our work goes exactly the other way. The largest returns to the particular types of investments that we've been studying are visible in the lower tail of the entry-level ability distribution and completely absent in the upper tail. Okay, thank you.
A paper where we're interested in the effect of years of education on earnings. And we have a lot of instruments. And sort of as in the literature started by Bound, Jaeger, Baker, and Steger Stock, it was shown that in that setting, two-stage least squares performs very poorly. And in fact, under some of the alternative asymptotics, in particular under the Becker asymptotics that allows the number of instruments to get large with the sample size, it was shown that two-stage least squares is consistent. Some of the other estimators that people have considered in this literature are consistent in that sense. Notably, Limmel is consistent and efficient, but some other estimators are also consistent. The bias-corrected two-stage least squares estimator proposed by Donald and Newey, the jackknife instrumental variables estimator, and some others. And so here, we want to start with from in that setting. We want to make two modifications to that. First one, sort of relatively minor, but it's important in the context of the application. In addition to allowing for the number of instruments to get large with the sample size, we're going to allow the number of exogenous variables to get large with the sample size. and I'll show in a minute when I get to when I talk about the application and the motivating example, why that's important. Essentially, in many cases where we have a lot of instruments, they're generated by interacting a single basic instrument with a lot of exogenous variables. And so if the number of instruments is viewed as getting large, we should probably also allow the number of exogenous variables to get large in that setting. That doesn't really change things very much. Limmel is still consistent and efficient, but we need to modify the bias-corrected two-stage least squares estimator and the jive estimator, and the standard errors also need some modification. But these are very minor changes to the existing estimators. The main contribution really is the second one, where we want to allow for the possibility that each separate instrument has a direct effect on the outcome. So each separate instrument is invalid, but there's a sense in which, on average, or in a typical sense, the instruments are valid. And that turns out to drive a wedge between Limmel and some of the other estimators. It turns out that as soon as there's some invalidity to these instruments, as soon as there's some direct effects of some of the instruments, Limmel becomes inconsistent. But by the bias corrected, the modification of the bias corrected and jive estimators remain consistent under much weaker conditions than required for Limmel. And in fact, we also end up suggesting some new estimators and some novel ways of identifying the effects of interest in that setting. So here's the motivating examples, and in fact there's two in the paper, but I'm only going to mention one in this presentation. This is from the Angrist and Kruger paper. They're interested in estimating the effect of years of education on log earnings. They use quarter of birth indicators as instruments, but in an attempt to get more precise estimates, they interact the quarter of birth indicators with state and year of birth indicators to get more instruments. And so they end up with a lot of instruments and a number of exogenous variables that is of the same order of magnitude, because all the additional instruments are generated by interacting these exogenous variables with the basic instruments. There's also concern that these instruments may be potentially misspecified. It may be that age at school entry affects academic performance and subsequent labor market performance. It may be that season of birth is related to socioeconomic status of the parents. These are all reasons that may make the quarter of birth indicators potentially correlated with the outcomes directly, other than through the years of education. So I'm going to skip the other example. Now let me move to the main setup. So initially we look at the case where the instruments are all valid. So we're going to look at a setting where we have the outcome y log of earnings in the Angrist-Kruger example that's linear in an endogenous regressor, the years of education, and linear in a number of exogenous variables. So in the Angrist-Kruger case, the quarter and state of birth indicators. Then we have a number of instruments coming from these quarter of birth indicators interacted with the exogenous variables here denoted by CI. So we're relating the endogenous variable linearly to the instruments and the exogenous variables. The number of instruments here is k, and that's indexed by the sample size, because we're going to look at a setting where we allow that to increase with the sample size, and the same for the number of exogenous regressors. To keep things simpler, we are going to assume normal homoscedastic errors, so some of the results can be generalized. Here, I'm going to need some additional notation, but this is pretty much most of that. So here are some of the previously considered estimators. One group of estimators referred to as the K-class estimators, which goes back to the late 50s, work by Nagar. Prominent members of that K-class are the two-stage least squares estimator, Limmel, and the bias-corrected two-stage least squares estimator proposed by Donald and Newey. And we'll introduce a new one here that's a slight modification of that. that adjusts also for the number of exogenous variable, and that's here denoted by the modified bias-corrected two-stage least squares estimator. Final piece of notation is the concentration parameter, which is something that measures the strength of the instruments. So that looks at the outer product of the first stage, taking out the exogenous variables. So C with subscript, this perpendicular sign, means after taking out the residuals from regressing on the exogenous variables, you look at the effect of the instruments on the first state in the first stage, and it gives you the strength of the instrument. Okay, so now what do we do in this setting? So the traditional textbook discussion sort of focuses on the case, and so one place where you can find it is in the Angrist book. That focuses on the case where the number of instruments as well as the number of exogenous variables is fixed. The first stage coefficients differ from zero, so the instruments do actually contribute something to the prediction of the endogenous variable, implying that the concentration parameter converges to some non-zero limit. In that case, all these estimators, Limmel, two-stage least squares, and the bias-corrected versions all are consistent, all converge to the same limit, and all have the same asymptotic distribution. Then, starting with the Steger, Stock, and Becker papers, people have looked at alternative asymptotics to get a better understanding of the different performance of some of these estimators in settings with weak and many instruments. So Steger, Stock look at the case where K and L and are still fixed, but they let the first stage coefficients go to zero with the sample size, implying that the concentration parameter converges to a non-zero constant only if you don't divide by the sample size, but the limiting object lambda 2 is actually equal to zero. They show how you can construct confidence intervals in that case, and they show that in particular Limmel does very poorly in that setting. The most relevant paper from our perspective is the one by Becker. Becker focuses on the case where pi12 is still the fixed for each element, but the number of instruments gets large, proportional to the sample size. Number of exogenous variables is fixed. And so in that case, a number of papers have shown that two-stage least squares is not consistent in this many instrument setting, but some of the other estimators are still consistent. Limmel, the bias-corrected two-stage least squares estimator, the modified version of that are all consistent because all of them have the property that the implicit value of k converges to 1 over 1 minus alpha k, whereas two-stage least squares with k fixed at 1 is not consistent. Okay, so now let me get to the first sort of novel set of results in the presentation. Here we want to extend that the many instrument asymptotics to allow the number of exogenous variables to also increase with the sample size. And the motivation is basically that in many settings where we have a lot of instruments, they're generated by having a very small number of basic instruments interacted with indicators for subpopulations or indicators for exogenous variables. So what we want to allow for is a possibility that ln increases with the sample size in such a way that the limit of ln over n converges to a constant, and allowing that constant to be positive. So the standard case would have alpha L be equal to 0. And so that leads to a small modification of the Chow-Swanson result, that now a k-class estimator is only consistent if k converges to 1 minus alpha L divided by 1 minus alpha L minus alpha k. And so the previous result in alpha L was 0. K needed to converge to 1 over 1 minus alpha k. Now that it needs to converge to a slightly different value. It turns out Limmel implicitly does that, and so Limmel doesn't require any modification, but the the original Donald Newey version of the bias-corrected two-stage least squares estimator does need to be modified, but this relatively minor modification gets us back to a consistent estimator. But Limmel still is the winner here. Limmel's still efficient in this case where all the instruments are valid, even if there's many exogenous variables. Now let me get to the main contribution of the paper. So what we want to allow for now is direct effects of all these instruments. So we're still in this setting where we have a lot of instruments. The dimension of C is equal to K sub n, growing proportionally to the sample size. But all these C's have non-zero coefficients in the outcome equation. So the previous case is a special case of this where gamma is equal to, where all elements of gamma are equal to 0. Now, it's useful to have a sort of augmented version of the concentration parameter. In addition to looking at the pi's multiplying the instruments, we also want to look at the inner product of gamma prime C. And we want to look at this 2x2 matrix here and look at the limiting values as n gets large. And so the first of the main, possibly the main result in the paper is that now the result for consistency for K-class estimators requires two things. One, K needs to converge to the same limit as before, 1 minus alpha L over 1 minus alpha L minus alpha K. But in addition, we need the 1,2 element of this augmented concentration parameter to be equal to 0. And so in general, without that, without lambda 1,2 being equal to 0, K-class estimators converge to the true value beta plus the ratio of lambda 1,2 over lambda 2,2. And so the implication is that the modified bias-corrected two-stage least squares estimator is consistent if lambda 1,2 is equal to 0. And so back for a second to the definition of this augmented concentration parameter. What is required for the consistency there is that the correlation or the product of these first stage coefficients of the instruments, the pi 1,2s and the gammas are 0 after some rescaling by the C's. And I'll interpret that rescaling in sort of a special case in a minute. But there's some version of the correlation between gamma and pi that needs to be 0 for consistency of these estimators. But most importantly, what is not required is that all the gammas are equal to 0 for these estimators. Limmel, on the other hand, is in general converges to something that differs from beta, unless both the lambda 1,2 and lambda 1,2 are equal to 0, implying that gamma is essentially equal to 0. So Limmel has requires much stronger conditions for consistency, essentially not allowing for the possibility of any direct effects of the instruments. And the intuition in the end is sort of fairly clear. If you look at what Limmel is doing, the way Limmel is defined, it tries to impose proportionality of all the reduced form coefficients, and that doesn't hold here. In this case, the beta is only equal to some ratio of the average value of the pi's and the gammas, but isn't equal to, but not all the reduced form ratios are equal to the parameter of interest. And by trying to impose that proportionality, Limmel is efficient if in fact that proportionality holds, but loses its attractive properties when there's some instruments that have direct effects on the outcome. Now, let me skip to the asymptotic normality part and let me look at a sort of special example to give some intuition for the conditions and then show how this actually works in practice. So I'm only going to look at one of these special cases, but both of them in the end have this group structure. that I think is a very natural one for generating many instrument examples. So we think of a setting where our sample can be partitioned into capital G groups. We have n sub G groups in each observations in each group, and we'll look at asymptotics where the number of groups gets large, but the number of observations per group, number of units per group is fixed, very much like a clustering type setting. And so we're going to look at ways in which the instruments are generated within the groups, and so now the number of instruments is going to grow equal to the number of groups, and so proportional to the sample size. So the setting we want to, so the specific case we want to look at here is one where we start off with a single instrument, and to do it in the spirit of the Angrist-Kruger example, we look at a single binary indicator, QI, that's the basic instrument. But then we have this partition of the population into these subpopulations, and we generate additional instruments by interacting the group indicator with this basic instrument. And so we're going to look at a setting where we have capital G groups leading to capital G exogenous variables, namely the group dummies, as well as capital G instruments based on the interaction of the original instrument with these group indicators. And for the first stage, we regressed the single endogenous variable, years of education, on the group indicators as well as the interactions of the group indicators and the instruments. Now, the Lambda matrix, this augmented concentration parameter, consists of two parts. It's the variance-covariance matrix of the gammas and the outer product of the two means, of the vector of means for gamma and pi. So in this case, the previous results shows that the modification of the bias-corrected two-stage least squares estimator is consistent if the 1-2 element of that matrix is equal to 0. That's not a very attractive assumption, or very plausible assumption in this case, because it essentially requires two things. It requires that the sum of the product of the means of gamma and pi plus their covariance is equal to 0. And it turns out in this case we don't actually need that. It's going to be sufficient if either we can still identify the parameter of interest if either the mean of the gammas is equal to 0, if the mean of the direct effects of the instrument on the outcome is equal to 0, or if the correlation between the direct effects of the instrument on the outcome and the direct effect of the instrument on the endogenous variable is equal to 0. And so let's kind of think, and so again, Limmel would require for consistency that gamma is equal to 0 for all units. The modified version of Jive and the bias-corrected two-stage least squares estimator would require that it essentially require that both mu gamma is equal to 0 and the covariance of gamma and pi is equal to 0. But we can further relax that by requiring only that the mean of gamma is equal to 0, or the covariance of pi and gamma is equal to 0. The first case, if the mean of the gammas is equal to 0, but the covariance of the gammas and the pi's is not equal to 0, then what we should do is drop all the interactions. What we should do in that case is simply use the single binary indicator Q as the instrument and not use the interactions. Adding the interactions would make Limmel and all the other estimators inconsistent in this case. The second case is the most interesting one. Suppose that in fact there's a common there's a mean value for gamma, meaning that the